Okay, welcome back. So I asked you to look into the idea of working out the mass from the velocities of galaxies moving around in a cluster. Okay, so come on, go back. There we go. So looking at this cluster here, where we could see the velocities all strung out along the line of sight. And at the beginning of the lecture, we measured that roughly as being 2,500 kilometers per second, or at least I did in my measurements. So if we use that as the V here, okay, so it's the sort of typical velocities that, I mean, this is quite high, that's quite a high velocity for a galaxy cluster, I must admit. But this, usually there are several hundreds of kilometers per second, but this is a very rich cluster. Okay, and asked you to take the size as 1 megaparsec, so that's 1 megaparsec there, okay, in meters, and there's big G. So that gives us 10 to the 45 kilograms, which is 7 times 10 to the 14 solar masses, okay. And in fact, the cluster in question on that stick diagram there, on the redshift slice, was the Coma cluster, and here's a little picture of it. Ignore the star here, but you can see just a real mass of galaxies here. There are easily many thousands of galaxies in here. So again, if you recall that galaxy like the Milky Way is at least 10 to the 11 solar masses, and then if you've got 1,000 of them, then you're going to be up at least 10 to the 14, if not more, solar masses in total. And of course, there's, as I mentioned, there's 10 times more dark matter in here as well. So there's a lot of dark matter holding this cluster together as all these galaxies are orbiting around in here. Okay, so we can use the velocities of the individual galaxies here, or at least the sort of typical velocity that they're moving around, to measure the mass of a cluster of galaxies to prove that there is dark matter in a cluster. Okay, so one final method to look at dark matter, and this is the sort of interesting idea of gravitational lensing. Okay, so this is the idea that light itself is bent by gravity. Okay, yet another prediction of Albert Einstein. And so here the idea is that we can use the amount by which light is bent to measure the mass of a cluster of galaxies, or even an individual galaxy. It works in both cases. Okay, and as you might imagine, it takes a lot of mass to bend light, so therefore it's suited to this sort of problem, and the geometry that can be found, because you've got foreground objects and background objects, works quite well in astronomy for this. And remember that light is bent by gravity, because even though it's the photon is a zero rest mass, it does have energy, and energy and mass are equivalent, so it is affected by gravity. So I'll show you a diagram in a moment, which makes this a lot more easy to understand. But basically, if you've got a background source of light and then a big mass in front of you, so between the geometry is very important here, so you need to get things lined up very well. So you need a background source of light, which in this case is a background galaxy, and then a foreground or a lensing galaxy that's going to do the lensing, or a cluster, so something with a big mass. And what you end up seeing is either a distorted or even multiple images of the background source. Okay, so let's have a look at a diagram, because it's much easier to understand that way. Okay, so this is the geometry that you need. Okay, so we're over here on the Earth as the observer, and you've got some background source a long way away, so like a distant galaxy. And here is a cluster of galaxies which is going to act like a lens. Okay, So light rays going straight through the middle are unaffected, but it's these light rays that are getting bent, so they would have carried on and missed the Earth, so we would never have seen them if this cluster wasn't here. But the cluster of galaxies is enough to, the mass in here is enough to bend the light a bit and bring it back into our line of sight over here. And if this is all perfectly symmetric, of course, you're going to do the same thing on the other side, okay? And so this is the idea, of course, so from our point of view, we think that light travels in straight lines. So we see another image of this background galaxy over here and over here, okay? Now, usually it's highly distorted, so, but sometimes you do just literally see multiple views of the same object. In fact, that's how lensing was discovered, really. Sort of pairs of usually quasars were found, and then if you look at the spectrum, they're exactly the same, and the chances of two objects being exactly the same was a bit weird. And then eventually, with a bit more work, people worked out that there was a foreground dense cluster of galaxies which was causing the multiple images of the background object, which was only one. Okay. So I'm going to keep things simple here. I'm just going to introduce a sort of typical distance away for the lens and assume that the distant galaxy is sort of a similar distance again, so that both we've got a DL here and here. Okay. The full formula is a bit more complicated, but let's keep things simple. So you can imagine actually if the distribution of matter in here is actually quite symmetric, like smooth, which of course normally it isn't, but imagine it is for a moment, you're actually going to get an image sort of everywhere in a ring around here. So this brings us to the idea of Einstein rings. And this is all linked to the idea that that geometry has to be very well aligned in order for any kind of gravitational lensing to work at all. Okay, so the background source, whatever's doing the lensing, whether it's a galaxy or a cluster of galaxies, and the observer, so all three must be very well aligned in a small angle. And again, Einstein worked out what this angle needs to be, and it basically is determined by mostly the mass. So you can see where we're going. If we can observe these things, then we can work out the mass and sort of how far away the lens is. So just geometry, really. Okay. And this is referred to as the Einstein ring radius. So this formula will give theta in radians. Okay. And as I'll show you in a moment, if you've got a very smooth sort of distribution of mass and basically you're spot on the axis and all three are perfectly aligned, you can end up with a pretty perfect ring. Okay, so again, this is where the name comes from. And then this angle here would be the sort of radius, angular radius of that ring. Okay. So let's put some numbers in here first. Okay. So why don't you calculate the Einstein ring radius? So use that formula and work out the Einstein ring radius caused by a typical galaxy. So here, just assume that you've got an individual galaxy, not a cluster of galaxies. So why don't you just assume 10 to the 11 solar masses for the mass of the galaxy and assume that it's 1,000 megaparsecs away, because usually these gravitational lensing type situations are using quite distant objects. Okay, so have a go at that, and we'll have a short break and come back. And if you can convert the answer to arc seconds, then that's much more useful.